Welcome to the deep dive. So today we're tackling a really interesting challenge in the AI world.
Mhm.
How do we get these smaller large language models to actually perform complex stuff like orchestration and picking the right tools, almost like the big ones do?
Right.
It wasn't long ago, that everyone was just focused on bigger is better, bigger models, more parameters.
Yeah, the race for scale.
Exactly. But now there's this real push to see how much we can squeeze out of these more streamlined, more accessible LLMs.
And that's the core question, isn't it? How can we, strategically constrain them,
Yeah.
guide them, so they can manage these intricate AI workflows like seasoned conductors?
Perfectly put. So this deep dive is all about exploring the different ways people are doing that,
Mhm.
guiding these smaller LLMs for orchestration, for tool selection.
Exactly. We've looked at recent research on LLM agents, how they use tools,
Yeah.
and insights from MLOps folks managing these things, plus a bunch of practical techniques.
Like fine-tuning, prompting
Yeah.
tricks, that sort of thing.
Yeah, precisely. Efficient fine-tuning, making sure they output structured data. Clever prompt engineering we'll touch on quite a bit.
Okay. And for you, our listener, whether you're just curious about what's happening at the cutting edge here, or maybe you're actually thinking about implementing some of these techniques yourself,
Uh-huh.
this should give you a pretty clear overview of what's going on. We're aiming for the key ideas without getting totally lost in the weeds.
Right. Keeping it accessible. We'll talk about frameworks you might heard of, maybe Connie or LangChain, ways to get structured output, like GBNF grammars,
Mm.
different planning approaches, too.
Sounds good. Okay, let's dive in then. Why is this even a problem? Why do smaller LLMs find orchestration and tool selection harder than the behemoths?
Well, that's the essential starting point, isn't it?
Yeah.
Unlike the really big models, smaller ones often have, well, less raw reasoning power.
Okay.
And crucially, smaller context windows. Think of it like trying to manage a big project with a smaller team that also has a really short memory.
Right, they can't keep as much information in mind at once.
Exactly. And when we talk orchestration, we're often talking about LLM-based agents, these AIs that need to interact with external tools, maybe control a robot, browse the web, analyze data.
Uh-huh. Interact with the real world or at least external systems.
Precisely. They need to plan, get feedback, adapt. But the smaller LLMs, they generally need more explicit guidance, more constraints to make sure they actually pick the right tool and complete the task effectively.
Okay, so they need more hand-holding, essentially. If that's the case, where do we start? How do we make them better orchestrators without just throwing massive amounts of resources at them?
A really key technique, and one that's gained a lot of traction, is parameter-efficient fine-tuning, PEFT for short.
PEFT.
The basic idea is adapting these smaller LLMs for specific jobs without having to do a full expensive retraining of the whole thing. And a super popular method within PEFT is LoRa.
Laura, low-rank adaptation.
You got it,
Oh.
LoRa. It's quite clever how it works.
So what's the magic behind Laura? Why is it so efficient?
Well, what's really neat is that it freezes the original model's weights. All that core knowledge it learned stays put, untouched.
Okay.
Then it injects these small trainable adapter matrices into certain layers, often the attention layers.
Ah, so you're only training these tiny extra bits.
Exactly. These adapters might only be, say, 1% to 10% of the total parameters. So you're training a tiny fraction, which drastically cuts down the compute and memory needed.
Makes sense. Especially for models up to what, 20 billion parameters, you said?
Yeah, it's particularly effective in that range. And here's another cool thing. LoRa plays really nicely with quantization.
Quantization. Okay, refresh my memory on that one.
Sure. Think of quantization as like compressing the model's numbers, its weights. Instead of using high precision numbers, you use lower precision ones, like 4-bit or 8-bit integers.
So less memory needed to store the model?
Precisely. And if you load the base model, already quantized, then add the LoRa adapters on top, you save even more memory during the fine-tuning step.
Wow, okay, so a double win on efficiency.
Yeah, and libraries from places like Hugging Face, like their PEFT and Troll libraries, make integrating LoRa and quantization surprisingly straightforward these days.
That sounds incredibly useful for tailoring these smaller models. But okay, we've adapted the model. Now for orchestration, using tools, how do we make sure it actually talks to those tools reliably? It needs to output stuff in a specific format, right? Like JSON or something.
You've nailed a really critical point there. Enforcing structured output. For an LLM to use an API or a function correctly, it often needs to generate its response in a very consistent, machine-readable format.
Right, can't just have it rambling.
Exactly, and this is where things like GBNF grammars come in. GBNF stands for GGML BNF. It's popular in the llama.cpp world, which is often used for running LLMs on, let's say, less powerful hardware.
GBNF. Sounds a bit technical. Can you give us the simpler version?
Absolutely. Think of GBNF as letting you define a really precise formal rulebook. A grammar. It dictates the exact structure the LLM's output must follow, down to the sequence of tokens or words.
So it's like giving it a super strict template it has to fill in.
That's a great way to put it. Gives you very fine-grained control. Now, you usually wouldn't write these complex GBNF rules by hand.
Okay.
You'd use wrapper libraries, things like llama CPP Python, or specific language bindings like llama Sharp. They let you define the structure you want in a more convenient way, and then they enforce it during generation.
Gotcha. So the tools handle the nitty-gritty of the grammar enforcement, but even defining it in a wrapper sounds like it could be tedious if you have many complex outputs.
It definitely can be. But the good news is there's automation for that too. Libraries like llama CP agent, for example, can actually generate the GBNF grammar automatically from higher level things,
Like what?
like pedantic models in Python, or even just from the signature of a Python function you want the LLM to be able to call.
Oh, that's handy. So you define your data structure or function, and it figures out the grammar to make the LLM output that.
Exactly. It massively simplifies getting reliable JSON output or enabling function calling, even if the Bates LLM wasn't specifically trained for it.
That's incredibly practical. Okay, so we have efficient adaptation with PFT and ways to force structured output with GBNF and these helper libraries. What about the step before that? Guiding the model to actually pick the right tool for the job. That feels like a major hurdle.
It absolutely is. And that's where prompt engineering becomes, well, absolutely crucial. Crafting effective prompts is essential to steer these smaller LLMs towards making the right choices about tools.
So what kind of prompts work best for this?
Well, there are several key strategies. One really basic but important one is just explicit instructions, telling the agent how and when it should think about using the tools you've given it.
Just spell it out clearly.
Yeah, and define any jargon or domain-specific terms it needs to understand. Another thing is providing guidelines or heuristics, like rules of thumb for tool use.
Okay, like if the user asks for recent data, use the search tool, that kind of thing.
Precisely. Another really powerful technique is few-shot examples.
Showing it examples of correct usage.
Exactly.
Right.
In the prompt itself, you show it. Here's a user request, and here's the correct way to call the tool with the right name and parameters.
Mm-hmm. Learning by example.
Right. And defining the agent's overall persona and objectives can also help guide its decisions implicitly. But maybe the most important part is that it's usually iterative.
Ah, trial and error.
Pretty much.
Yeah.
You test it, see where it messes up, and then you refine the prompts, or maybe even the tool descriptions, or maybe even the tool itself, based on what you saw.
So it's a continuous refinement loop. Makes sense. Okay, so we've got tools, structured output, prompting, but complex tasks often need multiple steps, right?
Yeah.
Planning. How do we get these smaller, constrained LLMs to handle that?
Planning is definitely critical. Smaller models often really benefit from breaking down big tasks into smaller, more manageable pieces. And there are a few ways to approach this.
Like what?
Well, the simplest is maybe prompt chaining, or what you could call fixed workflows. You predefine a sequence of LLM calls. Output from step 1 feeds into the prompt for step 2, and so on.
Okay, very linear.
Yeah. You can even stick programmatic checks in between steps. It's straightforward, gives you lots of control, but it's not very flexible if things go off script.
Right, it can't adapt easily. What about more adaptive planning?
For that, you can use agentic planning. Here, the LLM itself actually generates the plan. It decides the next step, which tool to use dynamically.
So you're trusting the LLM to be the planner.
Essentially, yes.
Yeah.
It offers way more flexibility, but you need really good prompt design to guide that planning process and make sure it can actually break the task down properly.
That sounds powerful, but tricky.
It can be. Another important idea is adding reflection or self-correction loops.
Making it check its own work.
Kind of. You build in steps where the agent, or maybe even a separate evaluator agent, looks at the progress, checks if the plan still makes sense, and potentially revises it or retries something. Techniques like self-reflection or multi-agent reflection fit here.
Interesting.
And finally, you can use structured planning frameworks. Maybe the most famous one is React.
React. Reason and act.
Exactly. It encourages the agent to alternate between reasoning about the task, thinking things through, and taking concrete actions, like using a tool. It provides a helpful structure for the process.
Okay, lots of options for planning. Now, if an agent is doing multiple steps using tools reflecting, it needs to remember stuff, right? What it did, what
Yeah.
the results were. How do we handle state or memory, especially with those small context windows we talked about?
State management. Yes, absolutely vital for anything beyond a single turn. The agent has to remember the conversation history, tool outputs, its current plan.
But the context window is small.
Right. That's the challenge. You can't just keep stuffing the entire history into every single prompt. It gets too long, too expensive, and eventually just breaks.
So how do agents cope? How do they remember effectively?
We often rely on what we call explicit memory architectures. This can involve short-term memory tricks,
Like,
like summarizing past turns, or selectively picking only the most relevant bits of recent history to include in the next prompt, trying to stay within the window.
okay, compressing or selecting.
Yeah. And then for longer term stuff or knowledge needed across many interactions, you use external systems. Vector databases are common, or knowledge graphs.
Retrieval augmented generation.
Exactly. RAG falls into this. You retrieve relevant info from this external long-term memory and inject it into the prompt just when it's needed.
So you have short-term working memory and long-term storage.
You can even have more complex setups like hierarchical memory combining different types. But the core principle behind all of this is selective context management.
Choosing what to put in the prompt.
Precisely. Deciding which bits of the agent's total state are most important for the next step, given those context window limits. It's a balancing act.
It really sounds like it. Like the agent needs to be strategic about its own memory. Okay, we've covered a lot of specific techniques. Are there bigger frameworks out there that try to bundle these ideas together for tool orchestration?
Oh, definitely. The whole area of LLM orchestration frameworks is exploding right now. LangChain is probably the most well-known.
Right, LangChain. Heard a lot about that.
It's an open source Python framework really focused on connecting LLMs to tools, data sources, managing prompts, building agentic workflows. It offers building blocks for a lot of what we've discussed.
Okay.
And there's this interesting observation floating around. Something like smarter agents need fewer constraints.
Meaning the really big models like GPT-4.
Yeah. Models like that can often handle complex tasks with simpler tool setups because they can do more of the reasoning internally, whereas dumber LLMs or maybe just smaller ones.
They need more explicit scaffolding, more defined tools, and stricter rules.
Exactly. You need to build more of the logic around the model with explicit tooling and constraints to get similar results.
That makes a lot of sense. What about other frameworks? I think I saw something about Redel, especially for multiple agents.
Redel's another interesting one, yeah. It's specifically designed for building these recursive multi-agent systems,
Recursive.
meaning agents can delegate tasks to other agents, potentially creating complex hierarchies. Redel is open source, event-driven, and built to handle these dynamic interactions between agents.
So for more complex collaborative workflows.
Potentially, yes. And some comparisons have shown it can actually outperform single-agent setups on tricky benchmarks, sometimes even pushing state-of-the-art, which is quite impressive.
Fascinating. So frameworks are evolving fast, but I also remember seeing chats, maybe on Reddit or forums, saying tool selection itself is still tricky, even with these frameworks. What are the common sticking points?
You're right. It's definitely not a solved problem. People run into issues. A few key things keep coming up.
Yeah.
Well, the quality of the tool description is huge. How clearly you explain what the tool does and its title. Also, how well you define the input parameters it needs.
Garbage in, garbage out for the tool description itself.
Kinda, yeah. And then there's the LLM's own reasoning ability, of course. The sheer number of tools you give it too many choices can confuse it. And the overall system instructions about how it should prioritize or use tools.
So it's a combination of how good the tools are described, how smart the LLM is, how many options it has, and the rules you give it.
Pretty much. Even with careful prompting, getting consistently perfect tool selection, especially with many tools, is still an active challenge.
Okay, one last area then. How can these systems check their own work, validate their actions or the output from tools?
Yeah, autonomous validation and feedback loops. That's becoming increasingly important. The core idea is using LLMs to check themselves or check the output of tools they've used.
How does that work in practice?
Well, you could have things like confidence-based invocation. The agent only calls a tool if it's sufficiently confident. Or you could set up specific validation workflows.
Like a dedicated checker.
Exactly.
Yeah.
Maybe a separate evaluator LLM, whose job is to look at an action or tool output and decide if it needs further validation. perhaps by calling another tool specifically for verification.
Using tools to check tools.
Right. And you can think of this validation as a form of feedback learning.
Hmm.
The main agent gets told, yes, that was correct, or no, that tool output seems wrong.
And it can use that feedback.
Yeah, either to revise its decision, change its plan for the next steps, or maybe even just learn, okay, that tool is unreliable in this situation. It helps refine both planning and execution.
Wow. Okay. This has been incredibly insightful, a real deep dive into making these smaller LLMs workhorse orchestrators. So, for you, our listener, the learner, what are the absolute key takeaways here?
I think the main things to remember are, first, the power of efficient fine-tuning, like LoRa, especially with quantization, to adapt models cheaply. Second, the need for structured output, using things like GBNF for reliable tool use.
Uh huh.
Third, strategic prompt engineering is absolutely vital: instructions, examples, iteration.
Hmm.
Fourth, choosing the right planning approach, whether it's simple chaining or more complex agentic methods like React.
Right.
And finally, smart state management, using short-term memory tricks and long-term storage like RAG to handle those context limits. It's really the combination of these techniques that let smaller models punch above their weight in orchestration.
That's a brilliant summary. Covers a lot of ground. And one really intriguing point that jumped out at me was that Riddell research you mentioned,
Ah, yeah.
showing that even by limiting the context for individual agents in a multi-agent setup, they could still outperform baselines and save costs. That's pretty counterintuitive, but highlights how effective these constraint methods can be.
It really does. Sometimes less context, used more intelligently, is better.
So, maybe a final thought to leave everyone mulling over. As these methods for constraining and guiding smaller LLMs get better and better, how might that change the whole equation? The relationship between model size and quote unquote intelligence, especially for complex workflows.
Hmm. Interesting question.
Could we see a future where highly specialized, super constrained small models actually become the go-to solution, maybe even outperforming the big generalist giants for specific orchestration
It's
jobs?
definitely something to think about. The trade-offs might shift significantly.
Absolutely. Well, that's a fascinating place to leave it. Thanks for joining us for this deep dive.